This is a pre-built version of the application. So let's go ahead and run it and do all the operations that are needed for this demo, and then I will go over what just happened. Now this is the equation of an elliptic curve over prime fields. So we perform all operations in mode P, where P is prime. And we want the values of x and y that result in this equation being satisfied. So for x is equal to 0, we end up with this result, and we have this result here and here. So we end up with those 2 points satisfying the equation. And for x is 3, we end up with this value, and it is the same here and here. So we end up with those 2 points also satisfying the equation. So we found 19 points that satisfy this equation, including the point at infinity, O. And we have a theorem that says that if we have a finite cyclic group with prime order, then all elements, meaning all points in this case, in that group are generators of that group, meaning all those points are primitive elements. So if we pick any point here, it will end up generating the entire group. And we picked this point, 5, 1, and it ended up generating the entire group 3 times. So each column is the entire group being generated. So we did 57 hops, and we can see the cyclic behavior here. So 5, 1 is repeated here, and 6, 3 is repeated here, etc. Now, if we had a huge number of points in the cyclic group, then we would not be able to do this, since it would take forever with slow hopping. So here we did fast hopping using the double and add algorithm. And I will go over how this works while writing and test running the application. So here we're doing 13 hops, and we ended up at this point. So 13G, this is the point, 16 and 4. And G is the generator point, 5, 1. Now before proceeding with the code, let's do a quick introduction. So this is Weierstrass equation for elliptic curve E over a field F, and we will be using this reduced form of that equation. So y squared is equal to x cubed plus ax plus b. And initially we will use f as the field of real numbers, and then to do cryptography we will use f as the field of integers in mode p. And those two curves are singular, so we don't want to use a singular curve, and a singular curve is when the discriminant delta is 0, so this value is 0, and a singular curve has repeated root. So we want to use a elliptic curve with a distinct root, like those two, this one and this one. Now looking at elliptic curves, we can make the following observations. One, that elliptic curve will always be symmetric about the x-axis. So if we have point P with coordinates x and y that satisfies the equation of the curve, then point minus P with coordinates x and minus y satisfies this equation also. And second, we can observe that the non-vertical, non-tangent line will always intersect the curve in 3 places. So given 2 points, for example P and Q here, we can construct a third point. And we can make the third observation that non-vertical tangent line will always intersect the curve in a second place here. So given 1 point on the curve and a tangent at that point, then we can construct a second point. And we can also observe that a vertical line will never intersect the curve in 3 places. And we can potentially take advantage of that fact in finding or defining a neutral element. Now we take advantage of our first and our second observations. So the symmetry about the x-axis and the non-vertical, non-tangent line always intersecting the curve in 3 places. So starting from 2 points, we can generate many points on the curve. So given 2 distinct points on the curve and the line joining them, let x0, y0 be the third intersection point of the curve with the line. Then we define addition of 2 points as p plus q is equal to x0 minus y0. And we also take advantage of our first and our third observation, so the symmetry and the non-vertical tangent line intersecting the curve in the second place. So this means that starting from 1 point, we can generate many points on the curve. So given P is any point on the curve with a tangent line to the curve at P, let x0, y0 be the intersection point of the curve with the line. Then we define point doubling as P plus P is equal to 2P is equal to x0 minus y0. And we also take advantage of our fourth observation that a vertical line will never intersect the curve in 3 places. So we define a neutral element O as an abstract point at infinity. So O is visualized as located toward plus infinity or minus infinity along the y-axis. And we also take advantage of our first and our fourth observations and the fact that minus P is the inverse of any group element P. So this means that P plus minus P is equal to O. Now those are the equations for elliptic curve point addition and elliptic curve point doubling, and I derived those equations in a previous quick tutorial. So we want to add the 2 points P and Q, and P with coordinates x1, y1, and Q with coordinates x2, y2. So we end up with point R with coordinates xr, yr, where xr is equal to x3 and yr is equal to minus y3, and x3, y3 is the third intersection point of the curve with the line. And here in the case of point doubling, we have P and Q are the same point, so x1, y1, x2, y2 are the same, and we have x3, y3 as the second intersection point. So 2P is equal to R with coordinates xr, yr, and xr is equal to x3 and yr is equal to minus y3. So the equations for xr and yr are the same for point addition and point doubling, and s is the slope, so it's equal to y2 minus y1 over x2 minus x1 for point addition, and for point doubling, s is equal to 3x1 squared plus a over 2y1, and s here is the slope of the tangent line through p x1 y1. Now we know that a group is a set with one operation and a corresponding inverse operation. So if that operation is addition, then the corresponding inverse operation is subtraction, and if that operation is multiplication, then the corresponding inverse operation is division, meaning multiplication with an inverse element. Now in order to have all four arithmetic operations, meaning addition, subtraction, multiplication, and division in one place, we need a field, meaning a set with an add group and a multiply group. So a field F is a set of elements such that all elements of F form an addition group with the plus as the group operations and 0 as the neutral element. And all elements of F except 0 form a multiplication group with multiplication group operation and 1 as the neutral element. And when mixing both group operations, then the distributive law does hold. So A times B plus C is equal to A times B plus A times C for all A, B, C in F. Now suppose that G is a set of points on E, including the point at infinity, and E is any elliptic curve defined over any field F. Now for all points A, B, and C in G, then the group operation is closed, meaning A plus B is equal to C, and they are all in G. And the group operation is associative, so A plus B plus C is equal to A plus B plus C, and we prove it here. So A plus B plus C, so if we take B plus C from here, we end up with this point, and then A plus B plus C, we have this intersection point, and we end up with this point as A plus B plus C. And here A plus B gives us this point here, A plus B, and from here to C we end up with this intersection point, and with this point A plus B plus C, and those 2 points are the same. And there is a group identity element, so A plus O is equal to O plus A is equal to A, And for all points A in G, there exists minus A in G, called the inverse of A, where A plus minus A is equal to minus A plus A is equal to O. And the group operation is commutative, so A plus B is equal to B plus A, and G, meaning the set of points on E, including the point at infinity, form an abelian group. Now, to do cryptography, we need to use a curve over a finite field, for example, a prime field, where all arithmetic is performed in mode prime number p. So an elliptic curve over Zp, where p is bigger than 3, is the set of all pairs x, y in Zp such that y squared is congruent to x cubed plus ax plus b in mode p, and a and b are in Zp, and O is an imaginary point at infinity, and this equation is different than 0 in mode p. So we end up with this elliptic curve point addition and this elliptic curve point doubling. So now we have mode P here, which we did not have here when we were over the real numbers. I will start by creating a new project. And here we will have 3 classes, and this will contain the elliptic curve logic, including point addition and doubling, and this class will represent a point on the curve, and this one will drive the application, so it will have a main method. Now here we will need 3 static methods, one to handle the pickup of the elliptic curve, so the values for A, B and P for the curve, and this one to handle the pickup of the generator point coordinates, and this one to handle the number of point hops, and if it is slow hopping or fast hopping, using the double and add algorithm. And we end up calling those methods from here. So here we are picking up the elliptic curve by calling the handle elliptic curve input, and here we are prompting the user to select what they want to do, is it slow hopping or fast hopping, using the double and add algorithm. And we call handle point hopping input from here. The user selected slow, or if he selected fast hopping from here. And here for convenience, let's specify those static values. And we want to use non-singular curves, so we want to avoid singular ones, and this is the case when a curve is singular, if this is equal to 0. So we check for that in this static method. And we want to keep track for the values for A, B, and P for the curve. And we use the constructor to initialize those. So now we can go back to the driver class and have this method finish the coding. So here we are checking if the elliptic curve is non-singular, and in that case we instantiate that curve. So here the curve to be instantiated is non-singular. And we display this in the case we have a singular elliptic curve. And here we handle the pickup of the generator point and making sure that what was entered by the user is a point that is on the curve. And here we prompted the user for A, B, and P and picked up those values. And we return the instantiated elliptic curve. And we will have two methods here. One for slow hopping, so slow multiply, given the number of hops. And this method can only be used with small cyclic subgroups. And this one for fast hopping using the double and add algorithm. Now a point on the curve will have x and y coordinates, and they are initialized in the constructor, and those are get methods. And let's define the point at infinity as having a huge y coordinate, and this is the equals and the toString methods for this class. So here we are checking if the passed in point and this point are the same, and here we are checking if we have points at infinity. And this returns the x and y coordinates for this point. Now those are the equations for point addition and point doubling. So this is slope, and this is xr and yr in both cases. And those two methods implement those equations. So this one does point addition, and this one point doubling. And we return the new point in both cases, which is the result of adding 2 points or doubling a point. And this is the toString method for this class. And those methods handle display. So this one handles display of the point matching table, and this one displaying all the points that are on the curve, and this one displaying the result of point hopping. And this method handles finding all the points that are on the curve, and this can only be used with a small number of points, otherwise it would go forever. So we are comparing the left side and the right side of the elliptic curve equation, and finding the points where both sides of the equation are equal, and returning all the points that we find, including the point at infinity. And this is a helper method to count the number of points that are on the curve, and this is the equation for the elliptic curve. Y squared is congruent to x cubed plus ax plus b in mod p. So if we want to determine if a point is on the curve, then we check both sides of that equation. So y squared in mod p and x cubed plus ax plus b in mod p. And this method checks to see if point G and point T are inverse of each other, so they are symmetric about the x-axis. And let's have the generator point as an instance variable, and it gets updated in this method given the user input. So now let's go back here and finish up this method. So we are prompting the user for the x and y coordinates of the generator point, and updating the elliptic curve with that point. Now before proceeding with finishing the code, let's go over this elliptic curve. Y square is congruent to x cubed plus 2x plus 3 in mod 97. So we found 100 points satisfying this equation, which means that the order of the elliptic curve is 100. And here we are using this generator point 3, 6, and those are the cyclic groups, or this is the cyclic group that it is generating. So it has 5 points and it is repeating. So n, the subgroup size is 5, and the cofactor h is the order of E over n, and this would be the cofactor. So now let's go up here and actually let's go here and add n and the order of E and the cofactor h. And let's add a get method for n, and if we go back to the constructor, we'll find all the points that are on the curve and count the number of points on the curve. This would be the order of E, and then we display all those points. And let's add this method that will give us n. So count number of points in cyclic subgroup given the generator point. So now going to the update method, here we can specify the value for the generator point and for n and for h. And this will implement the slow hopping. And this one, it implements the double and add algorithm to do fast hopping. So we turn the number of hops to binary, and if we have 1, then we add after doubling. And this should do it for this class. And this method here handles the point hopping. So we prompt the user for the number of point hops d, and if they already have selected slow hopping, then we call this method. Otherwise we do fast hopping with the double and add algorithm. And this should do it for this class. And finally, let's go ahead and test run the application. So let's try this curve where this is the value for A and this is for B and this is the value for P. And for x is 0, we end up with this value, and we end up with this value here for y is 7, and here for y is 22. So we have those 2 points satisfying the equation of the curve. So we end up with 37 points satisfying this elliptic curve equation, including the point at infinity, O. And let's use this as a generator point. So it generates the entire group. So the cofactor h is 1, so n is 37, and the order of e, or the number of points on the curve, is 37. So if we do slow hopping, and maybe 100 hops, so at the 100th hop we end up at this point, 5, 7. And we can see the cyclic behavior here. So each one of those columns, here and here and here, is generating the entire group. So let's try fast hopping and maybe do 32 hops. So we end up here using the double and add algorithm. And let's try 33 hops also. Just to show here the adding behavior. So we end up at this point. And let's change the curve, and let's show that we are checking if the curve is singular. So here we detected that we have a singular curve, and let's try this one. So we generated 42 points, or we have 42 points that satisfy this equation. And if we try this generator point and do slow hopping and maybe 25 hops, so we have 7 points in the subgroup, and the order of E was 42, and the cofactor is the order of E over N, which is 6. So if we do fast hopping, and let's go with 6 hops, So we end up here. So we had that points on an elliptic curve plus the point at infinity have cyclic subgroups, and this is where this subgroup here come from, or cyclic subgroup here. And if we have a finite cyclic group with a prime order, then all the points on the elliptic curve form a cyclic group. And this is where it applies. So here all the points form a cyclic group.